Hi everyone, Mrs. Belo here. In this video, I'm going to be going over the Chapter 3 notes on atomic structure, just the first half of these notes. So I thought this was pretty funny. Never trust an atom, they make up everything, because they literally make up everything. Again, an atom is the smallest particle of an element that maintains all the properties of the element. It is also the smallest unit of matter. As far as like high school science classes go, we'll just say an atom is the smallest unit of matter. And an atom, if you have an atom, it's going to be a specific type of element. It's going to be one of the elements on the periodic table. And in the web quest that you had for homework, again, make sure you check your answers against the key that's posted in the content library. You saw these 3 subatomic particles, look something like this, that make up the atom. So you should have noticed in the web quest that the proton was in the nucleus, and the nucleus, kind of like a nucleus of a cell, is located at the center of the atom. Okay, so everything in that circle there, kind of like the nucleus of a cell. And it has a charge that is positive. So when you were adding protons in the web quest, you should have noticed that the more protons you added, the more you increased that positive charge. And a proton does have mass. And these are so small. I mean, these are subatomic particles. These are things that make up atoms, which are the smallest unit of matter. And so we use special units for that. So a proton weighs 1 AMU. This stands for atomic mass unit. So it's a special unit that we use for atoms, which are really, really small. So in the middle here, you have your protons, which have a positive charge in the nucleus, and they do have mass. The other thing that you're going to find, the other subatomic particle in the nucleus, is the neutron. And as the name suggests, it is neutral. And like I said, it's also found in the nucleus. And like a proton, it also has a mass of 1 AMU. Now, in the web quest, you should have noticed that when you were adding these, it was changing the mass, but not what the substance was. So here's the web quest real quick. So I'm just going to do like lithium. Okay. 1, 2. Okay. So lithium has 3 protons. So again, if I'm taking away or adding protons, that's changing the identity of the element. So if you have 3 protons, that's lithium. 4 protons, that's beryllium, and then so on and so forth. Now, so it's the protons that are controlling the identity of the substance, like what element is it? Versus the neutrons, that's not going to change the identity of the substance. However, you could see that if I add and take away protons, that is changing the mass number. And same thing with neutrons. So those are found in the nucleus. And again, protons have positive charge. Neutrons don't have a charge. So if you look here, you could see that I have 4 protons. And overall, I have a charge of +4. So those have a positive charge. And then neutrons don't have a charge. Things that can also affect the charge are electrons. Electrons, they're not found in the nucleus. They orbit the nucleus. And they have a negative charge. And I know it says here they have a mass of 1 AMU. it is just such a small amount. Like it's almost it's negligible. Like it doesn't affect the overall mass really of the atom. So it's not really zero, it's just so close to zero that we call it zero. So if I go back here, you can see when I'm adding the electrons here. Hold on, let me just move. Oh, whatever. You can add the electrons, and notice that this is affecting the charge. If I have the same amount of protons and electrons, the overall charge is zero because they're canceling each other out. The positive and negatives cancel each other out. If I have one more proton, or one more electron, excuse me, than I do protons, I have an overall charge of -1. Versus if I have more protons than electrons, if I have one more proton than electrons, then I have an overall charge of +1. And note that the electrons, when we're adding those or taking them away, it's not affecting the mass, but it is affecting the charge. So the diagram here, we have the electrons, which are around the nucleus. Those have a negative charge. And oftentimes for an electron, I'll use this symbol. So if you ever see me write that, I'm just referring to an electron. And those have a negative charge, and they're around the nucleus. And then in the middle, we have the protons and neutrons that have mass that are in the nucleus in the middle. And the protons have a positive charge. And I'll get back to this model. This isn't the most current model of an atom. We have a more up-to-date model, but we still use it for teaching purposes. All right, so recall the law of conservation. So remember that matter and energy cannot be created or destroyed, okay? And when we're talking about matter, that's anything that has mass and occupies space, or it has volume. So it's made up of atoms. And in an ordinary chemical reaction, because if you get into nuclear chemistry, it gets kind of a little fuzzy with are you really creating or destroying an atom because you're breaking apart the nucleus. We're just going to talk about ordinary chemical reactions. Obey this law. And the same thing applies to energy. You can't create or destroy matter or energy, rather they change forms. So for example, if you look on the left-hand side, these are the reactants in a chemical reaction, and these are the products, or what is produced. And if you count the number of atoms on either side, you're going to see they're the same. The white is the hydrogens. There's 4 of those on either side. The black is the oxygen. There's the black is the carbon. There's 1 of those on either side. The red is the oxygen, and there's 4 of those on either side. So you didn't create or destroy anything. You just changed the form, or you rearrange things. And then if you were to burn something like a log, that energy, right, that there was stored energy in this log, and you're releasing that as heat. It's changing forms, but it's not like that energy didn't come from anything. It was stored a chemical energy inside of the log. All right, so now I'm going to get a little bit into the history of the atom. So there's a lot of different models that we've seen of the atom, and they have changed over time as we learn more about atoms and we've gained more data. We've had like more fancy equipment, or more just better ways to analyze certain pieces of data. And with that, we've been able to develop more accurate models of what an atom actually is. So we're going to start way back when, in the 1800s, when people were first starting to think about this. So, John Dalton first started thinking about, well, what is everything made of? There has to be something that is indivisible, like meaning it can't be divided anymore, that makes up the stuff in, our world and our universe. And so he proposed in the 1800s this solid sphere model. And he was just saying, like, there has to be something that, is the smallest unit, like that you can't make it any smaller. So he stated that all matter is made up of atoms. That was part of his theory. And all atoms of the same element are identical. Meaning, if you have an atom for carbon and another atom of carbon, they're identical. The exception is isotopes, which we will talk about later in this unit. He's stating the law of conservation of mass, that atoms cannot be created or destroyed. Again, kind of the exception is nuclear chemistry. Technically, you are breaking apart the nucleus. You're not destroying the protons or the neutrons. Rather, you're breaking apart the nucleus, which releases energy, nuclear energy, also a lot of radiation in that process. And then he also said that when we have a reaction, or we're talking about, we always form full number ratios. Okay. So you can't have half of an atom or something like that. They're always going to be in full number ratios. And these things can be rearranged. Again, kind of going with that law of conservation. And the word atom comes from the Greek word atomos, meaning indivisible. So again, he was stating that atoms were indivisible, like you couldn't divide them down any farther. And this was the unit that made up everything in the world and in the universe. Now, he was one of the first to recognize that, hey, there is something that you can't divide any further, and that atoms of a particular element differ from other elements. However, again, you can't really say they're totally indivisible, because they do have those three subatomic particles: protons, neutrons, and electrons. Protons, neutrons, and electrons. And then also there is nuclear chemistry as well, where you're breaking apart the nucleus, which releases a lot of energy in that process. In the next video, you will learn about the rest of the scientists and how this model of the atom went from this to this.